This is a 3-jaw chuck. No surprise, it has 3 jaws which move in a parallel and concentric motion when the chuck key is turned. This is the most basic way of clamping a workpiece on a metal lathe. If you have a metal lathe, it most likely came with a chuck like this. 3-jaw chucks are quick and easy to use, and for the most purposes they are the right choice. However, depending on which one you have, they are not the most accurate work holding on a lathe. Especially cheap ones, like the one here, have a significant run-out error. In this case, it's almost 1/10 of a millimeter. That's really not great, but luckily there are different and more accurate options. This is a 4-jaw chuck. No surprise, it has 4 jaws, which, in this case, move independent from each other. This not only gives you the opportunity to clamp weird-shaped parts, but also allows you to dial in your workpiece to almost 0 runout. The only drawback is that dialing in an independent 4-jaw chuck is very tedious and time-consuming, so you won't use this for repetitive or production work. But there's a third option which combines relatively high accuracy with easy handling. This is a collet chuck. And this is a collet. Collets come in all kinds of different shapes and sizes. This one here is an ER32 collet. The collet gets squeezed into the matching taper of the collet chuck with a lock nut from the front side. This compresses the collet and clamps the workpiece. This ER collet chuck is the most common and most affordable type for small import lathes like mine. If you are lucky to get a good one, you can get a relatively high and repeatable accuracy. In my case, with the part clamped, the runout error is about 0.02 of a millimeter. That's pretty acceptable, but what really bothers me on this chuck is that you need 2 different tools to clamp or unclamp your workpiece. And especially unclamping the part is a really violent task which shakes the whole machine around. So when, a few months ago, this beauty showed up on the used market, I just couldn't resist buying it. The blue boxes I'm digging out here are collets. And if you have seen the thumbnail, you already know I bought a new and special collet chuck. This new old chuck, even while bought on the used market, cost me about as much as I paid for the whole lathe back then. And if you're asking now, why would you even do this? Then this is probably the first video you're watching on this channel. So just don't ask and enjoy. This is a lever-operated quick collet chuck from the German manufacturer NANN. These chucks were still produced today. You can get them for about triple the price I paid for the used one, but of course without any collet. The chuck I got here is the smallest type in the series of lever-operated collet chucks from NANN. It is called SSF16, which at the same time indicates the maximum clamping diameter of 16 mm. Except from the handle, the chuck looks pretty much unused. Especially the collet seat shows absolutely no signs of wear. And that is, as it seems, for a good reason. Normally, the portion of the chuck with the handle attached should be free to slide back and forth in order to clamp or unclamp the workpiece. But in this case, no matter how hard I tried, it just doesn't want to move at all. It seems that something is wrong with this chuck. So that's the story of bringing this sticky collet chuck back to life and adapting it to fit onto my mini lathe. The first thing is trying to disassemble everything. As I don't want it to damage anything, I give all the parts a good soak in WD-40 and a night on the heater. My hope was that it's just some old and sticky grease and gunk which come loose with a little bit of heat and oil. But even with this treatment, there was absolutely no movement, at least with my bare hands. So I took a small hammer and gently tried to move the parts, but without any success. So I removed the hand lever and looked for something which might block the mechanism from moving. As I couldn't find anything, I just tried to separate the parts a little bit more violently. With the help of 2 wrenches, I finally could move the outer sleeve. A little bit of hammering and hand pressing finally separates the 2 parts. As far as I can see here, it's really just the old grease which got sticky and glued the 2 parts together. With the outer sleeve removed, you can see 6 hardened steel balls which transfer the clamping force onto an inner sleeve, which in turn presses the collet to the front against the collet nut and clamps the workpiece. This little screw prevents the inner ring from rotating and needs to be removed. Normally, the inner sleeve with the collet seat should slide freely back and forth. But again, when I push with my hands, there is absolutely no movement. This thing is totally stuck. I tried again with a lot of WD-40 and a little bit of hammering, but the inner sleeve just didn't want to move at all. So I took a scrap piece of aluminum in the right size and clamped the chuck in the bench vise. With this, I finally had enough power to move the inner sleeve. I got a few millimeters of movement until the inner sleeve bottomed out. But this is definitely way too tight for a functioning chuck. With a lot of hammering, I forced the inner sleeve millimeter by millimeter out of the chuck body. Even almost all the way out, it still sat extremely tight. But I finally got the inner sleeve out and had now all the parts disassembled and ready for cleaning. Before cleaning everything, I first checked the inner surfaces of the chuck body. They are all nicely ground and I couldn't find any imperfections or damages which may have caused the inner sleeve to bind up. And also on the inner sleeve itself, there are some discolorations, but nothing too extreme in my eyes. So I wiped away all the old grease before giving all the parts in a bath of alcohol for thorough cleaning. Thankfully, with a little bit of steel wool, I got rid of the old grease residues quite easily. I decided to remove the bronze bearing shells as well for cleaning underneath. But even with all the parts cleaned, the fit remained extremely tight. In the first half, it's a strong sliding fit, but with the sleeve fully inserted, it got stuck again. So that is definitely not how it's supposed to work. The sleeve itself seemed to be okay, but the lower part of the bore inside the chuck body seemed to be tighter than the rest of the bore. So I decided to fix this with carefully lapping the inner diameter of the bore on the back side of the chuck. I improvised this lap from a piece of aluminum, which I precisely turned to a close fit to the internal bore. I applied a very fine lapping compound and carefully lapped the inside of the bore. I regularly carefully cleaned everything and checked the fit. And that's the result of about half an hour of lapping. You can see two darker rings on the inside of the bore. I'm guessing that these were the high spots which made everything so tight. But I have no explanation why this could happen. As you can see, both parts have a really tight fit, and it's a little bit tricky to insert the inner sleeve. And you can also see that the sleeve is now free to move back and forth, while still having a very close tolerance fit. With this issue fixed and the chuck potentially working again, it is now time to adapt it to the machine spindle. The flange of the Collet chuck has a diameter of 69 mm and the flange on the machine has a diameter of 80 mm. So I have to make an adapting plate to fit the chuck to the machine spindle. I had this piece of 100 mm diameter and 10 mm thick steel flying around, which is ideal for making an adapting plate for the new chuck. I had to clamp the part in the 4-jaw chuck, as this is the only chuck I have which is large enough to clamp the plate. Because of the large diameter of the disc, I had to tilt the compound slide a little bit to get more reach. The first step is to clean the front face and establish a precise internal diameter to fit the spindle nose of the machine. I machined a large through hole on the flange, so it is possible to clamp bar stock later when the Collet chuck is installed. Now I am machining the centering collar, which has to have a really close fit on the spindle nose of the machine for minimum runout error. A last and very fine finishing cut, a little bit of chamfering, and the first side of the part is finished. Now I can remove the chuck with the plate still clamped and check for the fit on the spindle nose. And as it seems, the fit came out pretty accurate. I can feel no play in the arrangement. For the next operation, I have to mount the chuck on the rotary table to drill the bolt hole pattern. To mount the chuck on the rotary table, I made this adapting plate a while ago. Before I can drill the hole pattern, I have to dial in the part first to run through. I have to drill 3 holes to mount the adapting plate to the machine spindle and 4 holes to mount the Collet chuck onto the adapting plate. I only start tapping on the machine and finish the threads later by hand. Unfortunately, the 4 holes for mounting the Collet chuck onto the flange interfere with the centering collar, so I drilled it first with a 2mm drill bit and then widened the holes with a 4mm end mill. I don't remember why, but before widening the holes, I first finished the M6 threads. And now I have to widen the 4 holes to 4 mm. With this done, I can now mount the backplate directly onto the machine spindle for finished turning. But before, I remove all the burrs with a small stone. With the back surface nice and clean, I can screw in some M6 mounting bolts and screw the blade directly onto the machine spindle. As the blade is hard to grip by hand, I took the help of a face spanner. Now I can face the front side and turn the outer diameter down to about 80 mm. The last thing is to establish a precise centering collar for the collet chuck. The test fit with the collet chuck looks very promising. If you're wondering why the collet chuck is fully assembled again, I actually made the adapting plate before I disassembled and restored the collet chuck. I just switched the order here in the video for better understanding. For aesthetic reasons and to get rid of the sharp edge, I turned a large chamfer on the flange. The chamfer makes everything look a little bit more pleasant. Before removing the backplate for final finishing and assembling, I marked the current position in relation to the machine spindle. In this way, when remounting the chuck in this position, I should get a perfect run out. At least that's the theory. And that's the backplate in its current state. I just have to finish the 4 M5 threads for mounting the collet chuck on the plate. Again, I started the threads on the milling machine for perfect perpendicularity and finished them by hand. With that all done, I have now all the parts for final reassembling of the collet chuck. All the parts are nice and clean now and ready to be put together again. As the first step, I screwed the main collet chuck body onto the new made flange. Carefully cleaning of all the surfaces is very important here. The main body is secured on the flange with 4 M5 screws. Next I screwed in the small grub screw, which prevents the inner collet sleeve from rotating. This large key on the outside prevents the outer locking sleeve from unintentional rotation. A film of a very thin oil like WD-40 helps with inserting the inner collet sleeve. But due to the very tight tolerance fit, it is still not that trivial to get both parts together. A little bit of grease in the holes for the steel balls prevents them from falling out during assembly and helps for a smooth motion. The sliding surfaces on the outside get some grease too. The bronze bearing surfaces need to be cleaned carefully before reassembled with a light coat of WD-40. Now the outer clamping sleeve can be remounted and the collet chuck is almost complete again. Only the collet nut and the hand lever are missing. With the collet chuck now freshly restored and reassembled, there is still one thing left to do. In this stage, the hand lever is totally useless. It is just flying around with no function at all. The lever needs to be supported on the back end to function properly. So I need to make some sort of a support arm which connects the hand lever to the headstock of the lathe. A large plate of aluminum will give a good starting point. And yes, the saw blade seems to be ready for replacement. I removed most of the material on the bandsaw and cleaned the surfaces on the milling machine. The part needs a slot for a flat steel bar, which acts as a connecting rod between the lathe headstock and the hand clamping lever. I aimed for a very tight fit so that there is as little play as possible in the final mechanism. For the pivot bolt, I drilled and tapped a hole from above. With this done, it's time to bring the bracket into its final shape. To be able to mount the bracket as close as possible to the machine spindle, I machined away a circular portion of the part. I did this in a little bit sketchy setup on the lathe, with a turning tool mounted in the forge chuck. A little bit of material on the backside of the part has to be milled away, so that it is still possible to mount the chip tray of the lathe with a bracket in place. And that's the finished, rough-shaped aluminum bracket. Now I only had to make the connecting rod. It's a fairly simple part I made from a piece of flat steel bar. It just needs 2 bolt holes and a flat side to fit the hand clamping lever. And that's the finished rough-shaped connecting rod, ready for a first test fit. And that's how it's about to look like in the end. The bracket is supposed to take all the weight of the hand lever, so it is not resting on the chuck body itself, causing excessive friction or damage. Thus, the mechanism has to be made fairly precise and free of play. A short test fit on the machine itself to see if there is anything wrong with the design, before drilling the mounting holes on the bracket and on the machine itself. I tapped the mounting holes on the bracket at first, so that I can screw in some grab screws with a tapered end to mark the hole positions on the machine's headstock. With the hole positions marked, I can drill and tap the holes for 2 M5 screws. Adding the counter bores for the mounting screws in the bracket, and the parts are ready for assembly. As you can see, the hand lever is totally free floating and not pressing down on the chuck body. To make the parts look a little bit more pleasant, I gave them a few finishing touches. I rounded the ends of the part on the lathe, sanded all the surfaces nice and smooth, and chamfered all the sharp edges with a hand file. As a last step, I cold blued the steel bracket. And that's how the finished connecting rod looks like. In the background you can already see that I also modified the aluminum bracket to look a little bit more pleasant as well. And now it's time for final assembly on the lathe. I had to make a few cutouts on the chip tray, so it can be still mounted with a new bracket in place. I have to say that the chuck looks already pretty cool, but the question is, does it even work and how accurate is it? For the first test, I inserted the 6mm collet. You are supposed to give a little bit of grease on the mating surfaces, but even with that done, it's not that easy at all to insert the collet. Due to the tight tolerance fit, the collet tends to bind up. For the first clamping test, I inserted a piece of 6mm brass. The chuck now seems to work quite well and grips the part firmly. For testing the runout error of the chuck, I inserted a 6mm carbide end mill. To set the maximum clamping pressure, the manual advises you to screw the collet nut all the way in at first. In this position, the hand lever is almost locked and can't be pushed to the right. By slowly loosening the collet nut again, you look for the point where the hand lever can be pushed to the right in the close position. If that's the case, you have set the chuck to the maximum clamping pressure. To my surprise, the runout error in this configuration was surprisingly bad. The measured error was about 0.04 of a millimeter. That's not really what you expect from a high precision collet chuck. I mounted the chuck in the exact same position as I machined the flange, so I'm not really sure where the error came from. Without the collet inserted, I measured about the same runout error on the bare collet seat. So I decided to partly disassemble the chuck again and try to find a different hole position with a better runout. To not lose the steel balls when unscrewing the chuck body, I wrapped a piece of paper towel around it. So I unscrewed the chuck body from the flange and measured the runout on the bare flange. The reading on the centering collar was quite okay, about 1/100th of a millimeter. So I remount the chuck body and tried out all the 4 hole positions until finally, on the last try, I got a decent reading on the indicator. Somehow, rotating the chuck on the flange affects the runout on the front side. With the new mounting position of the chuck, I got less than 1/100th of a millimeter of runout error on the collet seat. With this issue fixed, I can reassemble the chuck again and make a final runout test with the end mill clamped. The runout error on the end mill shaft is now less than 1/100th of a millimeter. That is a pretty acceptable result. And if you're asking now, after this long video, what is so special about this type of chuck, I will show you here. This collet chuck both theoretically and practically allows you to clamp or unclamp the workpiece while the machine is still running. Of course, only if you're willing to lose a hand to the machine. But joke aside, this should be relatively safe and makes the chuck extremely useful when machining smaller series. I don't know how often I will use this feature, but it's better to have it than to need it. With this said, I hope you enjoyed this episode. Thank you all for watching. Until next.